Hello, everyone, and welcome to the Geek Nighter podcast. I am your host, Kaival Yapte, and I'm back with another episode. Today, we are going to talk about YugaByteDB, which is a cloud native distributed SQL database, which is Postgres compatible. We'll talk about the internals of database, how it works, how it supports ACID transactions, how it works in a distributed manner, and why Postgres compatibility matters. So, to do that, we have Frank from YugaByteDB with us. I've
Hi.
done an episode with Frank on database internals in general, and it was quite liked by our viewers. So thanks, Frank, for doing that, and thanks for joining us today. So welcome, and let's start with a little bit of introduction.
Yeah, thank you for having me. I really follow the podcast you are doing, going technical in many domains. That's really nice sharing that. I'm developer advocate for Yugabyte. I've been working with databases all of my life, a lot with Oracle, a lot as a consultant, but now I'm developer advocate, which means that I'm talking about Yugabyte, explaining to users, helping users to start with it and solve their problem, but also listening a lot to their problem or to what works or to possible enhancements. So all feedback welcome.
Yeah, awesome. Yeah. Your background in with the world of databases is amazing. As I started describing what is Yugabyte DB in one line, it sounds very simple: cloud native, distributed SQL, Postgres compatible database. And I want to dig a little bit deeper into each one of these. So, what do we mean by cloud native database?
Yeah, I think that's the most important question because cloud native can be used for many things. The idea of cloud native is that it's built to run in the cloud where things are running differently than on premises. On premises, you can have high-end hardware, you control the network. In the cloud, you have more commodity hardware that can
Hmm.
fail. But the advantage is that you can have lots of them and multiple availability zones. For example, a big difference is that cloud native, you take the advantage of having three data centers because that's possible in a cloud region. It's more difficult in on premises. So resilience that is needed when you are in the cloud, and also cost efficiency, the elasticity of it. If
Hmm.
you run in the cloud and you provision like on premises, you provision for the next year with the peak of activity, then you are not cloud native because it will cost a lot.
Yeah, that makes sense. And everyone wants this kind of redundancy, and many applications that are built today need multi-region support. So all these like cloud native features, if they are really native to also the database, I think that makes a lot of sense. What is distributed SQL then?
The idea of distributed SQL is different than sharding. When you want to scale out, run a database on more than one server for those
Hmm.
reasons, to be elastic, to be able to add new nodes or resilience, to have nodes still running when one is failing. When you want to do that, either you split the database, but then you split it to SQL databases. But globally, you don't see it as one SQL database because you
Hmm.
have to split it. The idea of distributed SQL is the opposite. You have SQL, you see a single logical database that runs on multiple nodes because data, but also SQL processing, also transactions are distributed on it.
Okay. Yeah, that makes sense. I want to go a little bit a step back there. So you mentioned like we want to scale databases, right? And that's when like the traditional database scaling comes into picture, where you want to create shards of databases, and so that you can have horizontal scaling. But that comes at a cost, because then these are really separate databases, and you are managing them as a separate database. And doing operations across these shards is really challenging. But when it comes to the world of distributed SQL, is it again based on sharding, or but it's just that the interface is different, or for being something distributed SQL, it needs to be distributed at all stack at each layer?
I We can say that there is some sharding. What I don't like when mentioning that is that people think that it is the difference is where you are sharding. At some point, you are sharding. At some point, you are taking the primary key and saying, oh, this key is going to this node, this key is going to another node. The
Hmm.
difference is that when you shard to SQL databases, like Citus, for example, you shard, and then you have GSQL. With distributed SQL, it's the opposite. You have SQL, and at a lower level, you are sharding. But you are sharding not to not to SQL databases. You are sharding to key values that hold the transaction intents, the table rows, the index entries. So you are sharding at a different level. That's different from sharding to databases.
Okay. Yeah,
So
that makes.
the terms are quite difficult because it can
Hmm.
also be called partitioning, but partitioning means something else in SQL. In
Yeah.
Yugabyte, for example, we are saying that we are sharding to tablets. That's
Okay.
the shards.
Okay. Yeah, and we'll go deeper there, like how an architecture looks like of when we create a database, for example. That's cool, and I think that makes sense. That has set up a foundation of for the discussion that we are going to have today. Like, what is distributed SQL? Why do we need it? Before we go really deep into the insert and the read queries and everything around that, I wanted to ask you, what is the problem it is trying to solve? So there is one problem that we already talked about. It's like scaling out the database. What are other problems that distributed SQL solves for our customers?
So first, about scaling out, people don't see the first problem. The need to scale out for performance because you cannot run on a single server because of the maximum CPU or memory. That's not the first one because you can
Hmm.
run a lot on a single instance. It may be expensive, but you can. The first thing is high availability and resilience. You scale out even a small database, you scale it out to be sure that if a server is down, if the network is down between a few nodes, then the database is still available. The first problem that it solves is resilience that you need everywhere if you care about data and the users of OLTP. But yeah, you need it everywhere. But in the cloud, for sure, you need it because those things will happen. Problems within a data center on premises, that doesn't happen too often. In the cloud, that happens. It may be
Yeah,
just a few seconds, but you don't want to break the application just because of that.
that makes sense. And we will dive a little bit deeper into how that fault tolerance is provided, how it impacts the performance and all that. Let's start with the very basic, right? Let's say we are talking about an e-commerce application where I have like customers, I have orders, and several other tables. And first of all, I want to onboard a customer. They are signing up and they want to create a profile. So they enter their name, email, whatever. And then let's say I'm backed up with YugaByteDB. So how does this transaction get saved into the database? And take us through the flow of data.
Yeah. So the architecture of Yugabyte is very similar to the architecture of Google Spanner that started with that, or CockroachDB or TIDB. The thing is that it's not directly distributed. First, you
Hmm.
connect. Many things are distributed. First, the connection. You need to connect somewhere, and that's the first thing. You can connect on any node. That's different from a, a single Postgres, which can have read replicas, but you cannot do everything in any replicas. So first,
Yeah.
you connect to any node. And there you have a Postgres backend that will process your query, which means that you are distributed because you distribute the connections. But once you have your session, you are on a single process. But
Mhm.
this single process does only the stateless stuff of SQL processing. So parsing the query, building the execution plan, and executing the execution plan. However, when it comes to read or write to a table, this is where there is another level of distribution from this single Postgres backend. The reads and writes are not local. They go to other nodes because the data is distributed. It can be local, but it can be on other nodes. So that's the difference, distributing the reads and the writes to multiple nodes. And then in those nodes, you have the partition, the shards, but they're also replicated. So those that we call tablets, but they're also replicated, which means that if you read from a node but this node is down, you can read from another one, basically. This is what is distributed. And a bit more complex, with SQL, you do not do only reads and writes, you do transactions. You have more than data reads and writes. So the data reads and writes are reading and writing table rows and index entries. But you need more. You have transaction intents. You have to put some log information. Depending on the isolation level, you have to say, I'm reading that. I want to that nobody touch it, or wait if someone is touch it. So there is more information than data itself. There is also the transaction status, because you are reading and writing, but everything you are doing must be done, but not visible yet until you commit. Then you need a place where you say, oh, this is committed. Other people can read it.
Okay.
And this is also distributed.
Exactly. Yeah. So it's not just about read, write. It's about the complex transactions and then the consistency guarantees. Sounds good. And so basically, if I understand correctly, when we are storing this customer object or the data into the table, it's again stored in what you call tablets. And these are replicated across, let's say, regions and for reliability and fault tolerance. But when I make a call to get the customer data, what I've written, it can go to any partition. And is that the case? Or there is a primary which takes care of handling that?
Yeah. Basically, you can not go to any nodes because there is one specific place for your shards, depending on which row. The rows are distributed on the primary key. The index entries are distributed on the index key. It can be by range or with a hash function. So if you need to read or write one specific row, you have to go to one specific tablet. And then this tablet has multiple replicas, but you cannot go to any one because if you want consistency, you need to read and write the same state. So you go to the leader. Those tablets are replicated with the Raft algorithm, where you write to the leader, and this is replicated to followers. And for performance, it doesn't wait for all followers. It waits for the majority of them, the quorum. So if you have replication factor 3, it waits for one follower that say, yeah, I got it. And then it cannot acknowledge the write. The thing is, if the majority has acknowledged, then you know that even if the leader is down, there is the latest state on one of those followers, and those followers can talk together to know which one has the latest one. So that's the thing. You always go to the leader. It is distributed because different rows have their leader in different places. But if you update the same row from many sessions, it will go into the same tablet.
Yeah.
You need also to think it's never really good, never really scalable to have an application that updates always the same row. You try to do a data model where you don't have that. Can be even worse in the distributed SQL because rows are distributed, but one row has a specific place. If not, you cannot be consistent.
That makes sense. That makes sense. And so to take an example, I have customer A. That customer, whenever I save that customer, it has let's say a customer ID, which is the primary key. And then that will go to a specific partition, which is the leader for that row.
Yeah.
And then if I have customer B, which has another customer ID, that can go to a different tablet or a different partition, which is the leader for that row. And so how do I specify based on what key I have to partition? Is it the primary key by?
It is always the primary key. Actually, the table columns are all stored in their primary key. More like SQL Server or MySQL, different from Postgres heap tables. So they all go on the primary key, and this is on what it is sharded, and the index is sharded on its key. So you just define a primary key. If you don't define a primary key, you can, because you can do it in Postgres. Then to be compatible, we can do it. But then it will introduce a primary key, a UID, that will not be very useful. So makes sense to always have a primary key. And also to think, if you have the choice between multiple keys, to set the primary key to the one that will be used the most by critical queries. Customer ID is probably a good one there. And then by default, so the key can be one or multiple colons. And by default, we apply a hash function on the first one because it's easier. With a hash function, you can directly distribute. You don't need to wait to see the range of values to distribute it. However, if you use a hash value on it, you can use it for queries with an equality, but not with a range. So a customer ID, you probably don't query a range of customer ID because the ID you have generated it.
Yeah.
So that's probably okay to use a hash function. But for example, if you have a timestamp in the key or in an index key, there are good chances that there is a query on a range of dates or time. And then you prefer to do range sharding, which will start with one shard and then it will be split when it grows. And to mention that, we use the index syntax where you say ascending or descending on the columns in an index. So if you say nothing, it will be hashed. And if you say ascending or descending, it will be ranged and then also stored within each tablet in ascending or descending order.
Okay, that makes sense. And this is similar to the clustering key that we talk about in NoSQL, some of the NoSQL databases, right? Based on which it is kept sorted, so range queries are faster. Okay.
Actually, in a key, you can have both. You can have the first columns that are hashed and the next one that are with a range. And that's exactly like NoSQL partitioning key and clustering key. You want to distribute on some value, but on some other, you want to cluster them. For example, your customer orders, you probably want to have them together for the same customer and date. And
that makes sense. That makes sense. Cool. Going back to the write path again. So when I'm writing, it's assigned to a leader based on the primary key, and then it is also replicated for durability and fault tolerance. How is it written to the disk? What is happening there? Is it written to the memory first and then like a write ahead log, and then it is replicated based on that? And how does that replication actually works?
Yeah, that's very specific to distributed SQL. The first thing I will mention is that you go to the leader, but if a node is down, the leader there will be stepped down and new leaders will be elected elsewhere. That happens because each tablet, independently, the tablets talk to their followers through heartbeats. And then when it is detected that there is no heartbeat for 3 seconds, then there is a new leader election. So the Postgres backend knows where is the leader, but if it doesn't answer, it can immediately retry the read and write to the follower, and this is how it is resilient. So then what happens on the leader? For read, that's easy, just reading. For write, we are used to traditional databases that store tables and indexes in BTrees or heap tables plus BTrees. And BTrees are quite good for monolithic databases because a BTree, when you insert, has to go to a specific block and update it. And that works when this update doesn't need an IO. And with the BTree structure, you have most of the blocks that stay in memory. The thing when you distribute, you cannot distribute the memory, is local to each server. So a BTree structure is not well suited to be distributed. Here, there is the replication with the Raft logs. So the writes are replicated. And those logs are used to update the tables and the indexes, which are stored as LSM tree. And a LSM tree is an append-only structure on different levels. And the first level is in memory. So the thing is that if you do an insert, you just have to write the new row. If you do an update, you just have to write the new value. And this goes first into a buffer in memory in the server where the tablet leader is. Because it is only in memory and you don't want that it crashes, it is protected by WAL, write ahead logging. So this log is written. But this log is also sent to the followers so that they can update their followers. The same kind of log sent by the Raft algorithm. And the followers will also apply it and log it. Because if a server is down, the follower needs to have it. And then the followers acknowledge. And the leader, so the leader has written the log, and the leader waits for the majority of the follower to say, yeah, I've written it. And then it writes it to its own memory structure and can acknowledge the write to the client. And then there is another phase, but that comes asynchronously, where it says, okay, I acknowledged it. And then it is acknowledged kind of to phase commit protocol, but this is asynchronous. So to summarize, we have logs, so the changes, like event streaming, the new values, the new rows that are going to memory, also to disk with the role. But then this memories happens. You have all the new changes. And at some point, you don't want this memory to be too high. And then this is flushed. When you write, typically the default is maximum 28 megabytes per tablet. Maybe I should mention that tablets, the goal is that a table is sharded to tablets that are 2 gigabytes, 10 gigabytes, not something too big. And for those 10 megabytes, you have the memory structure, the mem table, the first level of the LSM tree. And then it is flushed to files that are called SST file. And the interesting thing with those SST files is that when they are written, they are never touched. That's very different from the data files in Oracle in Postgres, where updates will take a block, get it in a buffer, update it, write it again. Here, when it is flushed, it stays there. The new changes go to memory and may be flushed to another file.
Got it.
And then at some point, you have too many files and there is a background compaction happening, because at some point you don't want all intermediate values. Usually in a SQL database, you want intermediate values for the past 15 minutes, past hour, because you may have queries that need to see something consistent as of a specific point in time. But after some time, you don't need those intermediate values. So if you have updated the same row 10 times, at some point you don't want to see the 10 intermediate values.
Yeah.
So that's the compaction. So that's about the write.
Right.
If we think about the reads, when you start with an empty table, everything goes into memory, so that's easy to read. This memory structure has some kind of indexes in it. And then it is flushed to files, which means that when you want to read a specific key, you have to see if it is there in the memory structure and in the multiple files. And that's the reason why we also need to compact it, not only for the space amplification where it takes space, but for the read and amplification. Because if you have 100 of files where your key may be, then that's too much. There are many optimization in the LSM tree. The implementation is based on RocksDB. There are many optimization like Bloom filters and internal indexes where most of the time, even if you have a lot of files, it knows that those files cannot contain the key, but at some point it needs to be compacted.
That makes sense. So I want to summarize because there is a lot of things, a lot of details, right? I want to validate my understanding. So we talked about there is a leader. Whenever I write a row, there is a primary key based on which a leader is selected, and then it's replicated. The way it is replicated is based on the logs. And then when the leader gets acknowledgement from majority of the replicas, it also writes it to memory. It's not B-tree implementation, it's LSM based implementation. And because it's distributed and then it's written to the memory first and then later to the data file, and then there can be multiple such files. To avoid having too many files, we also have this merge and the compaction level. The underlying data store is RocksDB. And did I miss something there? But overall, I think it makes sense the way it works, why we are replicating. And this is synchronous replication because you want to have consistent writes and reads.
to a quorum,
Okay.
to the majority.
Yeah. Okay. Cool. I think that makes sense. And so the underlying structure is based on LSM trees and it uses RocksDB. I've seen RocksDB being used by many other databases as well. Like a little bit on that, what are your thoughts? Like why RocksDB is suitable for such use cases?
I think the first reasons, one reason is also that the founders of Yugabyte have been working on Cassandra, on
Mm,
Hatch-based, and then have seen and optimized RocksDB for this. RocksDB is very good for small databases, not big one. Doesn't really scale for big ones.
mhm.
But because we shard to tablets where we know the size, if it goes beyond 10 gigabytes, it is split.
Okay.
Then you are sure that each tablet is a RocksDB that works on the size where it works quite well. So
Okay.
that's very interesting. I see also, of course, there are pros and cons when compared to BTrees. I see a big advantage. The fact that you write to a file and never touch it again.
Mhm.
This lowers a lot the risk of disk corruption because corruption happens usually when a block is read and written, and for whatever reason the written value to disk is not the exact one.
Mhm.
If you write it once and you are sure it is okay because you have a checksum, if nobody reads and writes it, then you reduce a lot the risk of corruption. So that's also
Mm.
interesting. And I see also another big advantage that we use for the backups that we do for point-in-time recovery. You don't really need a backup for failures because you have replication, but for point-in-time recovery, for user failure, for example, you drop a table, you want to get back to 1 hour ago, you need backups. And because those SST files are written and never touched, it's very easy to have incremental backups
Mm.
because an incremental backup is just the new SST file since the last one that you have backed. You don't
Yeah.
have, for example, in Oracle, to do an incremental backup, it has to read the whole database to write the changes. There are some optimization that marks which blocks can have changed, but basically it has to build the incremental. Here we have the incremental just because there are new files. So those
Mm.
are advantages. Of course, there are also some cons. For example, the read amplification. You have to read from multiple files. And this is where in Yugabyte, it's based on RocksDB, but with lot of improvement for reads, like the Bloom filters, like some indexes, like very simple things. If for SST file, you store the min and max value for a column, then at least given the query, maybe you
Mm.
know that in this file, no need to read it. You know that there is no value like that. And yeah, those are very useful because first RocksDB was more something very optimized for writes, like in Cassandra, because you just happen to a
Yeah.
structure, then that's
Yeah.
fast to write and reads maybe slower. And yeah, I should add something also. SQL is more complex than everything. First, there are transactions, and yeah, we will talk about that just later. The picture that I've done with the way reads and writes are just reads and writes. We need to, we have another level of complexity because of transactions, but that's also something when you insert a row, this is not a single write. Because if you insert a row in a table, it probably has a primary key and maybe some unique indexes. And in SQL, you have to read the value first to see if it already exists, to be able to raise a duplicate key exception. If you think B is fast to write and then insert should be fast, yes, but inserts in SQL need also to read. So there is this need to optimize the read.
Okay. Yeah. Okay. That makes sense. And that's a very good point, right? Because even for writing, you have to also optimize the reads, as you mentioned, just to have this kind of constraint, the
Yeah.
unique key violation and all that. Otherwise, if we just append, there might be data corruption because it's not unique anymore.
Yeah.
That makes sense. And so to make it clear, we use RocksDB as the storage engine. And so the actual relation or the data model that I picturize for a customer object, it's actually stored in a key value manner. Is that correct?
Yeah.
And so the key is customer ID, and then the value is each of the columns, or is it?
And the value can be each of the column, or there is an optimization that packed all the columns in one value to make it easier. And with this optimization that is now by default on all versions. So if you insert a row, you have the key that is the primary key value and the value that is all the packed columns. But if you update a single column, then you have the new version that has the key and only the value for the column. And the
Got it.
compaction can also put it back to a row. So this is very useful. Before this feature, it was quite difficult with tables with a lot of rows. That's also something that comes with SQL and especially Postgres compatibility. When you are Postgres compatible, you have tons of applications. And there are applications with tables with 5 columns, but there are also applications with tables with thousands of columns. So yeah, you need to be up for them. Yeah.
Needs a balance. Yeah, that makes sense. And okay, we talked a bit about read optimization and how YugaByteDB uses Bloom filters and some indexes too. So the idea is basically to reduce as many IO as we can. So it's faster, it's all in memory. Or even if you are going to the disk, you are reading as low number of pages as you can, right? And that's the reason Bloom filters are used for optimization, to avoid any page reads which you know that I'm not going to find the data there. So that makes sense. On the tablet side, I just wanted to clarify. So you mentioned two things here. Like one is 10 gigabytes and the other one is 128 megabytes. So
Yep.
these are two sizes. And if I get it correctly, so 128 megabyte is for one tablet. And then you split
It's
across
the memory, the first level in memory for one tablet. Yeah.
Okay. And then the 10 gigabytes, what is that constraint?
That's the maximum size for a tablet before it is automatically splitted.
Okay.
So, for example, if you sort by range, because you know that you will have range queries, usually you start with a single tablet and then you add new values. And then when it reaches some threshold, it will split it. It's not a strong limit. It's more, it makes sense to split it, to keep it in a size that is good for RocksDB, but also a size that is good for all the tablet management that can happen. For example, if you add a new node to the cluster, there is some rebalancing. Some leaders and followers will be moved to the new node, first adding new replicas and then electing leaders. Moving 10 gigabytes is okay. You don't want to move terabytes in that case, for example.
Okay. So is it a move to a different node, or it's just a different tablet and it's just like a logical separation between the two?
There is a load balancer that always look at the tablets to see if this is balanced in the number of tablets, but also in the number of leaders, because leaders take reads and writes. So you want also that to be balanced and ensures that it is balanced. Of course, by default, it tries to balance everything, to distribute everything, but you have also the possibility to add some placement specification. For example, there are some tables or some table partitions that you want to be only in one region because it stores your customers from Europe and you have to store it in Europe. And then the load balancer will take that into account when rebalancing. But maybe we can add a level of complexity there. When I said that one tablet is one memory table and one LSM tree, it is actually two. Because here we need to introduce the transactions that we have in SQL. If we directly write when we are doing inserts, updates, deletes, delete is just a write of a tombstone saying for this key, the row doesn't exist anymore at this timestamp. When we are doing all that, we cannot, the most important thing, all those changes, all those logs have a timestamp. In SQL, you need to say, this is the new value as of this point in time, so that the queries can do consistent reads And depending on the start of their read or their transaction, they read as of a specific point in time. So
Got it.
everything you write must have a timestamp. But the timestamp is the commit timestamp, because it's at commit where you say it is visible.
It is visible.
And that's the tricky thing in SQL. You are writing changes. You have to put a timestamp, but you don't know it yet. And that's a big difference with NoSQL. Even if NoSQL have transactions, there are only one command where you know the timestamp. In SQL, the application or the user can say begin transaction, read something, update, insert, take a decision on what it is read, and at the end will commit. And everything that was done must magically have this commit timestamp. Some databases do that by coming back to change the timestamp when it is committed, either synchronously, but that can take time if you changed a lot of rows, or later asynchronously. And what we do with Yugabyte, we have an additional level in each tablet for that, where everything that a transaction is reading or writing goes to a first LSM tree with its memory table and SSD file that holds only the transaction intents, the provisional records, not yet to the final database. And when you commit, in the background, those will be moved to the final regular database, the final RocksDB, where it has the commit timestamp, which means that when you read, actually, I said that you have to read from memory table and maybe multiple SSD files, but you have also to read from the intents to see if someone has changed the value and committed it before your transaction, and then you need to see this change, or simply to see that someone is updating the value but didn't commit yet. And then you have either to wait or to fail, saying it's not serializable, but you need to know what the other transactions are doing, and this goes to the intents. And it's the same structure, LSM tree with memory table and SSD file. In practice, there are no SSD file because intents are small and usually fit in that 128 memory. In practice, it's more like a memory buffer, protected also with write-ahead logging, but with a very long transaction, it can also go to file. So we have this level where the writes go to an intent DB. And also, the transaction needs to set a status somewhere. So there is a transaction table. That is also a tablet that references those intents. And because when you say commit, you don't want to wait for the move of those provisional records to the regular ones. So you just set the status, and the concurrent reads can see if it's committed or not. And in the background, it will be applied by each tablet. So there is a transaction table, and more than one, because the goal is to keep it the most local as possible. When your transaction touches only one node, because all your rows were in that node, the transaction table is in this node with no need for network call. If it touches other nodes, but in the same region, it will use a transaction table in the same region, because if you explicitly say my data is in Europe, you don't want to update a status in US just to say that it is committed in Europe. So yeah, there is this transaction table, but that's the main thing and the big difference with sharded databases like Citus, for example, or Oracle Sharding. They have only local transaction table, which means that they cannot have a consistent read on top of it, knowing exactly what is committed or not. It can be inconsistent between the nodes. Here, because we have the transaction table that is also distributed and protected, the same as a tablet, then we are fully hosted on top of that.
Oh, I see.
And this transaction table being also protected with replicas means that if a node is down, even if it's a node that holds some transaction information, this is still available elsewhere. In many databases, even if there is a fast failover, all transactions are rolled back and must be started again. Here, the transaction just continues because the provisional record were replicated, the transaction status was replicated, and then everything just continues.
Okay. That makes sense. Is the transaction table one table for all the tables, or it's for each table one transaction table?
Between that, it can work with only one transaction table, but then there is a problem of locality. If you are distributed multiple region, you want a local transaction table, and it can be upgraded because that's the point. With SQL, you don't know what the transaction will do after. So maybe the transaction will start touching a table that you have pinned on the specific region, and then you want the transaction table to be there. And then you update a table that is in another region, and this transaction table must be visible in the other region. So there are a few ones that are automatically managed.
Got it. And what was the reason? I guess you mentioned briefly that so we need this as a separate table and not we can't mark it in the same table. So just to go a little bit back, I guess this idea is similar to how Postgres does it with MVCC, right? To have a separate version, and then the XID is identifying what transaction it belongs to and who committed this transaction, and that makes it visible. And it's part of the same table, if I remember correctly. So what what is the difference if it was a part of the same table, that this is the latest value and this is the transaction, versus having it in a separate table like transactions table?
Actually, I think you need both because
Okay.
you want to know for one transaction, you want to know everything that it has changed. For example, if you are updating many tables and at the end you say rollback,
Yeah.
you
Okay.
need this transaction table to know which table and which tablet it is.
Yeah.
And then for each table or for each tablet, there is an internal index of this transaction has done those writes, and a two-way references. There is a kind of reverse index saying this transaction has done this write, and this write was part of this transaction.
Okay.
And that's in the instance DB, so usually in memory. But you need also, the transaction table is not only the status. The transaction table must also know where are the actual read intents or writes that have been done by this transaction, because you may need to roll back them.
Yeah. Okay. Yeah. And transaction, it can span across multiple tables and can be really complex. So yeah, that is definitely more information that we need there. Cool. And is it similar to MVCC though? Is it done to avoid locking, and if there are a lot of concurrent updates? So it basically creates a new version for any row that someone is trying to update. And then that has some ID. And then at the end, once the transaction is committed, all those new versions of different tables or different rows become visible.
And this ID is a timestamp. An hybrid logical clock, we need more than an ID. We need an ID with an order.
Yeah.
That's the thing also in SQL. You need to have the sequence of changes. If not, you cannot do anything consistent.
Yeah.
And because it is distributed, you need a clock that is ordered even when there are changes in different nodes, which may have a different physical clock, because the physical clock, even if synchronized by NTP, there is a clock skew between them. If you have atomic clocks in your data center, you can have that shorter, but there is still a skew possibility. So we have this hybrid logical clock that is based on the physical clock, but adding a Lamport clock that increases the value each time messages are exchanged between the nodes. And this gives a clock that will be always increasing and that can be ordered. So that's basically in RocksDB, the key is the primary key of the table plus the timestamp.
Okay.
And that's MVCC, and by default, but that's configuration. By default, we keep 15 minutes of intermediate changes, and after you don't really need them for MVCC, but that can be configured also depending of your long queries. Yeah, basically the same idea as MVCC in Postgres, for example, but not having this transaction ID wraparound because we have this clock that always increases.
Yeah.
And not having the timestamp plus the transaction ID is actually the timestamp.
The timestamp. That makes sense. That makes sense. Cool. And yeah, I guess it's clear. What is the default like isolation level that Yugabyte supports? Is it serializable isolation or is something like Postgres?
We support all isolation level as Postgres just because you need it to be Postgres compatible.
Yeah.
For the moment, but that will change in future versions. Because of compatibility, for the moment, you have to set a parameter to get the read committed by default because it was implemented later. But the idea is to have the read committed by default because it is the default in Postgres and you can change it. Of course, if you switch to serializable, there is more information that is written because the reads are also writes.
Yeah.
With serializable, you must write the intent of reading so that other transactions knows what you have read and can check if it conflicts.
Okay.
So that
So something
goes
like something like select for update, right? Like you're reading, but you're doing it to update something. So it's like taking a lock.
yeah, but in read committed, you explicitly say select for update. You want that. In serializable, you just read.
Yeah. Okay.
And that's the database that keeps track of everything that we have read to detect the conflicts. In this
That
intent
makes
DB,
sense.
if you are in serializable, you have more information in it.
Okay. Yeah. I imagine the complexity there. That makes sense. And we already touched like how transactions work. You have this like a clock which you can use as a transaction ID along with the primary key of the row. And that's how MVCC is done. But where does like ACID comes into picture and what does it mean that it's ACID compliant in a distributed manner as well?
Yeah, ACID compliant means that it is consistent even for the most complex transactions. And even a single insert is complex because if there are secondary indexes, you need to update them. So there are multiple writes that must be visible at the same time. And and a transaction can join tables, can do many things on many tables with many indexes. So basically writing those intents and the transaction status, this is the way to be ACID at global level without restriction. All indexes are global. When you shard to multiple databases, you cannot have a global unique index to guarantee that something is unique across the nodes because the transactions are local and cannot update an index that may have entries in multiple nodes. Here, all indexes are local. So you can have a global index, the primary key, but secondary index can be unique. And then you have all ACID properties. And also for reads, there are some databases that shard where the writes are committed at the same time using a two-phase commit that will go to all nodes and say it is committed. But the reads, if there is not this global transaction table saying that, yes, these changes are committed or not, then if you read from multiple nodes, you may read something inconsistent, which means that you are joining a table with its parent table, but maybe you don't see the new parent insert and you may have something that is not consistent.
Okay.
So to be fully SQL distributed and fully ACID, you really need to have SQL on top of the distribution, not breaking the SQL query to multiple tables, because at some point the SQL transaction, if you break it, you don't have the same ACID properties.
Okay. And yeah, like many NoSQL databases also say that ACID compliance comes into picture, but there is a limited ACID that we get because there is no SQL on top of it. And SQL adds the complexity is what I understand.
Yeah, they are transactional, but saying ACID doesn't take the real meaning of ACID complex transactions. What NoSQL do is they simplify what you can do. For example, I think that most of NoSQL databases, the global indexes are not consistent. They are maintained asynchronously. you don't have unique constraints. You don't have foreign keys. So you reduce the operations to single reads and writes. And
Got it.
actually, we can do that also in Yugabyte. We can disable some of those IC properties. For example, I mentioned that when you insert data, you have to read also. And that takes time, of course. But if you are just starting a new database and you have to bulk load into an empty table, you don't want to read because you know that the set you load is already unique.
Yeah.
So this is where you disable those transactional features. We call that non-transactional, where you do the same SQL, but without this acidity. It will not check. Someone may read the partial insert before the commit, but you don't care because if it's the initial load, nobody is reading it at the same time. And in Yugabyte, the most important API is the Postgres compatible one with all SQL features. But there is also a Cassandra-like API where you can move your application written for Cassandra, you can move it, but then you have also the choice to have these ACID properties or not. You can say this table is transactional, and then it will use the intense DB to do something transactional. So the idea is rather than having a NoSQL database and NoSQL database, the idea is to have a database that can do all. And for specific cases, you may have better performance by disabling some ACID properties, and then you can.
Okay. So basically, YugaByteDB can be a distributed SQL and a NoSQL database as well, depending on your use case and your guarantees that you need. Okay, that makes sense.
The idea is really to optimize for SQL, but yeah, for migration, if you migrate by loading a very big database, you don't want to enable ACID as long as you are only loading and you don't have the application running on it. So.
That makes sense. Cool. Let's talk a little bit on the fault tolerance part. So as you mentioned, whenever I'm writing, it's going to the leader, but it's also replicated to the replicas. And then these replicas to be fault tolerant across different regions. I want these replicas to exist in different regions, right? So when I create a table, how do I specify this that, okay, I want this kind of replication. I want protection against a region failure. For some data or for some use cases, I might not want this table to be replicated across region because I care more about performance, but I want it within the same region. So is there a way I can do it while creating the table, or how does it work?
So the default is to distribute, but also when you start a new Yugabyte node, you tell it on which zone, region, cloud it is, because it can be on multiple cloud providers. So each node knows where it is.
Okay.
And then your decision will be to say, I want to replicate across multiple regions. And that's the load balancer, the one that looks at how the tablets are balanced and maybe moving them will take care of your specification on that. So there is a default for the cluster. Then you just create tables and they will use the default. If you deploy in a single region, multiple availability zone, you want one replica on each availability zone. If you deploy on multiple regions, then you have this choice. And this choice can also be made by table. Actually, we use the Postgres table spaces for that. So Postgres has table spaces, which are used in Postgres to go to different file systems. We don't need that because we don't store in local file system. We store on the network. So we use table spaces where we mentioned placement info for the table spaces. For example, I can create a table space that will replicate to multiple regions and maybe guarantee that there is one replica in each region. I can create a table space that I call Europe that will be only on 3 availability zones in Europe. And then I will map the tables, the indexes, or the table partitions to the table space. Those partitions are not the shards. Those are the Postgres declarative partitions, where you say, my customer table, there is the country ID. This list of countries will be in the table space Europe. And then you guarantee not only for performance, but also for data governance, you guarantee that your data is in Europe. Means that my European user will have the lowest latency and will be guaranteed that no data goes to US. using table spaces with that. And of course, this can also be changed to move some data to one place to the other. And in addition to the placement of replicas and the fault tolerance, so this is
Hmm.
where you define fault tolerance to a navigability zone or a region. In addition to that, you can also set preferred leaders. By default, the leaders are distributed because they take the reads and writes, so you than the followers, and you want to distribute that. But that means also that if you are on multiple regions, some rows will be closed, some rows will have a higher latency. And by setting some preferences, you can say all the leaders are in Europe. I have followers in US and in Asia. And then at least all my reads, the reads go only to the leaders, and all the reads are local. The writes will have to wait to one of them. If you say Europe, US, and another region in Europe, then probably the reads will be fast because the first to acknowledge is
Yeah,
the other region in Europe, unless there is a region failure and the application still works, but with higher latency. So
that makes
setting
sense.
leader preferences can make sense also.
Yeah, that makes sense. One fun fact that I did an episode with Dennis on geo distributed application, and where we talked about this data governance and GDPR policies, where you don't want your data to go beyond a certain geographical location. So you can all do that. So for our viewers, if you're interested, please go and watch after you watch this episode. Cool. And I also did a podcast on Postgres compatibility, like how it's important and what are the levels of different Postgres compatibility. And we also demoed it with YugaByteDB and CockroachDB and Spanner and Aurora and all that. So it's also an interesting watch. So on that, I want to ask you, in your experience, like being Postgres compatible is a big win because all the existing Postgres applications can actually move seamlessly or without much pain to YugaByteDB, right? And it improves the adoption where people feel confident that, okay, they can do it and without any surprises at the runtime, for example. In your experience, is it true? Do people feel confident when we say it's Postgres compatible? And what about folks who are MySQL compatible, for example, or they're using MySQL and they want to migrate to a distributed SQL, or they are totally on NoSQL and they want to migrate to distributed SQL because they want ACID. So how is the different like level of confidence and where does it come from?
What I've seen, because we have this architecture with those two layers, the query layer where we use Postgres or the Cassandra API on top of the storage, the architecture would allow us to build a MySQL query layer. But the thing is that nobody is really asking for that.
Okay.
So those who use MySQL for workloads where it makes sense to use MySQL, maybe websites or WordPress, either they don't need to go to distributed SQL, or there is also TIDB. There are also other solutions. But in OLTP, given the many features of Postgres, those who move prefer to rewrite the application. Rewrite can be a full rewrite or just changing the dialect in Hibernate and looking at a few queries. So the effort can be very different depending on the application. But they usually want to move to something Postgres also, because it's not only about reusing application written for Postgres, it's also using a database that is very popular, where you find a lot of information. If you have a question about how to do that in SQL, you will not ask how to do that in Yugabyte because
Yeah.
there are not so many users as compared to Postgres. But because it's compatible, you just look in Stack Overflow how to do that with Postgres, and that will work in Yugabyte. So the knowledge base is already there and very useful. So even if someone is used to MySQL, learning Postgres is not that difficult. And it's also, this is part of modernizing the IT, and it's also quite good to go to something that is more close to the SQL standard.
Yeah.
And it also opens all the Postgres compatible databases. They
Hmm.
may move to Yugabyte and maybe someday want to change to something else. They can go to Community Postgres, they can go to Aurora, they can go to AlloyDB. Going to Postgres compatible, making the application Postgres compatible opens a lot of different databases.
Yeah, that's a great point. What is what is the future of distributed SQL? So it's becoming more and more popular. People are facing problems. Let's say either they are sharding the Postgres infrastructure and there are operational challenges, or they are using NoSQL databases where they still need ACID, but there's a lot of overhead on the application level. So they want their database to do the heavy lifting and also be distributed. So I think the adoption is growing, but what is the future like? Like, what kind of applications would move to something like distributed SQL or like Yugabyte?
I think we see multiple ones. First, going to the cloud and to
Hmm.
cloud to manage service. That's also something. When you manage your own database on premises,
Mm.
you can ask your DBA team to do a maintenance on the weekend. When you go to the cloud and to manage services, if you want to lower the cost, you have to accept the maintenance window or the failures of your cloud provider.
Yeah.
But if you go to a cloud native database that is resilient, then you can have a managed service that is never down and can be upgraded
Mm.
without stopping the application, which is important. If you go to a managed service, you don't want a team of DBAs with an on-call rotation because there is a failure during the night and you have to call someone. You
Yeah.
want something that is just resilient.
Mm.
So this is one thing, going to distributed SQL for that. What we see also is that Postgres is evolving a lot in many features like SQL features, but there are still some problems that are not easy to solve in an old database because you cannot change completely the storage of
Yeah.
a database that is used. And being open source, it's even used for critical use cases without real support. So the risk to break something is more important. And we can do things with a new database like Yugabyte. We can do things that Postgres cannot do, or we can do it faster. Not even related to the fact that it is distributed. We have a new storage engine. For example, the transaction ID wraparound. We don't have this problem because we use a timestamp. The MVCC implementation, we don't need to vacuum. We
Mm.
have a background compaction, but that's really in the background with no impact on the current transactions. There are also many Postgres problems that are solved by going to a new database. I'm not saying that it solves all problems without bringing new ones, but at least those ones are solved. So we see also people moving because they're okay going to a new database and getting rid of the old problems they have. But also with this guarantee that if it's not okay, they can also move back to Postgres if they want,
Mm.
because they don't have to change something in their application to
Mm.
run on Yugabyte. The most thing that they can have to change is think about the data modeling. But what you do on the data modeling will still be a good practice on analytic database. Because if you want to reduce, I don't know, if you want to reduce the reading too many rows, for example, you do it because in a distributed database, there is some additional latency. But that's good in any database. If you don't need all rows, don't read all rows. Use there is still valuable, even if they want to move to something else.
Yeah, that makes sense. Cool. So I think YugaByteDB is a great choice when people want to move from Postgres or any other database and they need distributed SQL, ACID transactions. But what is the what are the applications that are not suitable for something like YugaByteDB?
Yeah, of course, there are. The first focus is OLTP for
Mm.
two reasons. First, because everything is optimized for OLTP like transactions, the
Mm.
access by primary key, because of this structure in the LSM tree, storing the table within the primary key. That's very good for OLTP transactions.
Yeah.
And the other reason is also that for data warehouse, you may not need all those ACID features. So if you are doing only analytics, there are other solutions that may not be fully ACID, but you don't care, and may have more optimizations for that.
Mm.
However, we are still optimizing for analytic queries because even OLTP application, they have some analytic queries.
Yeah.
And you don't want to move all your data to a real-time data warehouse, for example. So we are doing some optimization there. Mostly those are called pushdowns, means that by default with this architecture, if you just have this key value storage and on top of it Postgres, means that if you want just to do a count star from a table, this architecture would say, okay, read all the rows, get them to the Postgres backend, a single process, and then count them here, which is not efficient, of course. So this is where we have push downs. It's not only read the rows, it's read the rows, but count them and just give me the count. And then you have a partial count that you just have to sum. And that makes sense because if you distribute to multiple nodes, you don't want to do the compute on a single process.
On a single node. Yeah.
But those are case by case. The count
Mhm.
star, for example, is an old push down, but we have a recent one. For example, if you select distinct, you don't want to get all rows and deduplicate them in a single process. You just want to ask each node, each tablet, what are the distinct values for this column? And then you still deduplicate, but on something that was already deduplicated. So there are
Okay.
some optimizations for that. We have also materialized views. We have also the features that come from with Postgres. And if you need to move data to another database that is more suited for analytics, we have changed data capture using Debezium and through Kafka, for example. And yeah, that's another solution. You have your operational database, and to do the analytics, you want to do some kind of event streaming, going to a database that doesn't need all these acid properties. Maybe you don't need a replication factor 3 for this one.
Yeah. Okay. Yeah, that sounds like covering most of the use cases, but for, let's say, analytics purpose or data warehousing, I think it might not be the best suited one, at least yet. Maybe in future, I don't know if that is in the plan, but
that evolves a lot. For
yeah.
example, today many people are asking for PG vector to
Mm.
index the embeddings to do some AI, and that doesn't look like no LTP workload. But there are some use cases in OLTP where it can be useful, and we are also implementing that. Yeah.
Perfect. Yeah. Amazing. As usual, Frank, your experience with databases is remarkable, and thanks for sharing all the insights that you have. And I definitely learn whenever I talk to you and whenever I even follow on you on Twitter. So for our viewers, please follow Frank and always sharing some amazing tips and interesting blog posts. So do that. This was insightful. And if our viewers are interested in general database internals, I did an episode with Frank last year. So please take a look. I'll attach that in the description. And thanks a lot, Frank, for sharing your insights and experience. And that was really amazing.
Thank you very much.